Our experiment was how flower orientation affects wing beat frequency in an unexpected way in butterflies.
First, we kind of started making some observations of different animals while we were out in the field, and we started to look at, or thinking about this idea of optimal foraging, which has to do with getting the most energy out of your foraging. And so in this, there are two different scenarios we have set up, where there's a hummingbird at rest on a twig, and then a hummingbird that is hovering. Both of them are foraging and consuming food, nectar from these flowers, but the butterfly or the hummingbird that is hovering is going to be using more energy because it's having to stay in flight and use its wings to balance itself. So optimal foraging has to do all with energy gain and optimizing energy gain. And they say that you should forage the least costly way when energy available is low. While certain spots have more energy available, it's all about finding that balance of the correct distance to go, or the shortest distance to go, while getting the greatest amount of energy out of that traveling time. And a part of the optimal foraging theory is the marginal value theorem, which has to do with animals leaving an area when energy gain has dropped to the average gain of the area. So when food resources are, when they're not going to be getting enough energy out of their trip, or they're not going to be maximizing their energy out of their trip, then they should find somewhere else to get food. So it all can be kind of summed up with one equation, which has to do with the net energy equaling the energy gained minus the energy lost while foraging.
And for our analogy, we have a rock climber hanging on the wall, which is kind of like he's spitting energy, he's stabilizing himself, and he's trying to spend as least energy as possible to stabilize himself. And on the right we have a person going on the ground, which kind of represents like the flower horizontally of how a person's going to spend less energy. And with the butterfly is going to be stabilizing itself, maybe beating its wings to have the ability to pick up the nectar or the energy. And on the right we have the butterfly that's spending less energy foraging and picking up the energy it needs.
Okay, so this brought a question for us, which was why waste energy beating wings while foraging to stabilize itself? So why would a butterfly hover and flap its wings more to forage and use more energy than what it's gaining? And so that brought our hypothesis, which is butterflies will beat their wings more on a vertical flower than a horizontal flower, because on a vertical flower we thought that they would flap their wings more to stabilize itself than on a horizontal flower. And this is what our graph or our data would look like if our hypothesis were true. The horizontal flower would have less wing flaps than a vertical flower.
We actually conducted our experiment in the gardens behind Grand River Chapel in Gano Chapel, located at William Jewell College, as well as Burr Oak Woods Nature Center, located in Blue Springs, Missouri. We chose these locations because they were highly diverse in flower populations and also had a high presence of butterflies. Also, the flowers there were still alive, so that was a high factor in it. So first, when we went out in September 2017 to October 2017, and during the day from about 12 p.m. to 4 p.m. in the afternoon. When we went out, we first took the temperature using a thermometer and recorded it in a log, as well as wind presence. Then, using an iPad, we took videos for about 15 to 30 seconds of butterflies on a flower. Once we were done taking the videos, we used a clinometer to actually measure the angle of the flower that the butterfly was on. If the angle was 0 to 45 degrees, it was considered a horizontal flower, but if it was 46 to 90 degrees, it would be considered a vertical flower. Once we collected all of our data, we actually went back and analyzed the videos, and we counted the wing beats per minute. So we decided that a wing beat was going to be any movement from the wings that would return to its original position, and here is an example video. So as you can see, we would consider these wing beats because it's returning to its original position. To actually analyze our data, we used 2 ANOVA tests. We used a one-way test, which considered only one effect, or one variable, against the wing beat frequency that we saw in the video. So this would be the flower orientation, the temperature, and the wind presence. And we also did a 2-way ANOVA test, which considers 2 variables, or 2 factors, dependent on the wing beat frequency. So in this, it was actually going to be the interaction of flower orientation and temperature with the wing beat frequency.
Okay, so this graph is just what we showed earlier, what our hypothesis should yield, so lower wing beat frequency on the horizontal flowers. What we actually found was that butterflies were beating their wings more on horizontal flowers and less on vertical flowers, and these results were significant because our p-value was 0.00992. We did a one-way ANOVA on temperature, on the effective temperature on the number of wing beats per minute, and our results were significant because our p-value was 0.0468, but we didn't find a very meaningful effect because the only real difference is this value down here, which is much lower, and these 4 were all pretty close to the same. We also did an ANOVA to look at the effect of wind presence on the number of wing beats per minute, and these results were not significant because our p-value was 0.899, and as you can see, the results pretty much yield the same thing for absence of wind and presence of wind, and the number of wing beats didn't really have an effect. So the last ANOVA we did was a 2-way ANOVA to test the effect of interaction of temperature and flower orientation on the number of wing beats per minute, and flower orientation was significant because our p-value was 0.0095. However, temperature and the interaction between temperature and orientation were not significant, and our p-value for temperature was 0.14608, and then our p-value for the interaction between the two was 0.86243. So this is the first graph we showed, but opposite of what our hypothesis predicted. So butterflies will beat their wings more on vertical flowers, which did not support our hypothesis, and there was a significant variation between wing beats on flower orientation. It was just opposite what we thought. So we determined that it was not a stability mechanism. So we considered other things that could have maybe affected why our results would be opposite what we predicted. So one thing we looked at was wind. Like when we were filming our videos, a lot of us noticed how wind was we would get some strong gusts and the wind would kind of flow the flower. So we thought maybe those on horizontal flowers would be more affected by the breeze coming right over them, and thus they would have to beat their wings more for stability, but as that ANOVA showed, it was not significant. We also considered temperature, but we did not, like I said, we did not really find a meaningful result, even though our results were significant. So the last thing we considered was thermoregulation. Since butterflies are ectotherms, and we took our videos at around midday every time, the sun would have been like directly above the flower, so those on the horizontal flowers would have more direct sunlight beating down on them than those on the vertical flowers. And we found out that the scales on butterflies' wings are used to dissipate heat, so we thought that maybe those on the horizontal flowers would be beating their wings more to dissipate heat since they're receiving more direct sunlight. And that's just a zoomed in picture of like the butterfly scales. So this idea kind of relates to how lizards thermoregulate. So early in the morning, a lizard might be like burrowed in the ground so that it's retaining body temperature. But around midday, when the sun is coming straight down, the lizard might have to move to a shadier spot so that the body temperature does not rise significantly. And around late afternoon, when temperatures are still pretty high, the lizard will be aimed towards the sun so that the least amount of surface area will be like facing the sun to maintain a better body temperature. So our next step would be to test the effect of body temperature on the number of wing beats on both horizontal and vertical flowers. And so based on what we considered, we would predict that there would be more wing beats on horizontal flowers like what we got. And we could do this by measuring the internal body temperature of the butterfly after collecting the number of wing beats per minute.
We'd like to thank the William Jewell College Biology Department for lending us the resources and the lab equipment we needed as well as the lab space, and then as well as Dr. Paul Klawinski and Professor Nickel for assisting us with analyzing our results and just support throughout the process. Questions?
Does wing or wing shape like affect their beats per minute for butterflies, or is that not really matter?
What did you say? I just didn't catch the
Because
beginning of
of
that.
shape.
Okay.
Is the wing shape of the butterfly.
I just- We didn't really find anything related to wing shape, so I guess I don't know.
That's a good question.
That's a good question.
That would be something to consider though.
Yeah.
Yes.
Did you record videos of butterflies in the sun and in the shade?
We did not because we thought it was just a stability mechanism, so weren't really considering sunlight presence when we did the experiment.
That would probably be something we implement into the next steps.
Yeah.
How might you do that? Talk about a design.
I think at least using Weather Channel's predictions of what the temperatures are supposed to be and what the weather's supposed to be. Look for days where it's going to be sunny, and look for days going to be cloudy, and kind of shoot to have windows where it's going to be around the same temperature, but one with sun presence and one with cloud cover, and record the same videos and then kind of compare on those days.
There is some difficulty in that
Yeah.
because a lot of days when we had to go out mostly on sunny days because if we went out and looked on a
There
cloudy
was
day, we didn't
no
really see
butterflies.
any butterflies.
So,
Because we were doing, maybe if you did it like more in like June or July,
Yeah,
when temperatures
warmer
are still
time.
high, since we were getting into like October when it's starting to cool down, especially if the sun isn't really as present, that could be a reason why we didn't see any butterflies when it was cloudier.
So what would be a better design?
To not do it in October.
yeah.
But to take off Aubrey's suggestion, so I would not advocate doing it on sunny days and then doing it on cloudy days. I would advocate doing something else. What would be a better thing to do?
Would it be doing the research in a lab to where we can control at least the temperature, to where butterflies would still be active in a
control
false
light.
ecosystem? Yeah.
Yeah, we
You
could
could control
control
light
the amount of
availability.
shade and light availability.
Can you not control the amount of shade out in the field?
I would love
You
to-
could just,
yeah,
like,
I was gonna
cover
say,
it.
you could get
Yeah.
a shaded area.
You could just
And-
put a piece of paper on
I
the
mean-
flower.
Yeah, sure. Just carry an umbrella. And
Yeah.
shade certain flowers and not shade certain flowers.
Yeah.
Then you can do them all under the same weather conditions. The only thing that you're really altering is direct radiant heat from the sun.
More questions?
How does flapping wings help dissipate heat? Go back to your figure of the scales on the wings of the butterfly. Yeah. What does flapping gain you?
When the butterfly flaps its wings, it's actually releasing its internal temperature, cooling it down inside.
But how? Explain the biophysics of it to me.
When the wings are flapping, the wind is circulating under the wings and back out the body.
What are those scales doing?
Are they lifting up and down as wind
I
comes
don't
out?
think they're opening it. So you've got more air circulation. Where do you need to circulate that air? On a butterfly's wings to dissipate heat.
Towards
Question.
towards like the body.
So what? So you guys talk about dissipating heat. What in Zhao et al. 2010 did they talk about in terms of how butterfly scales are used to dissipate heat? You should guys figure this out if this is your major alternative explanation for why your data turned out the way they did. Because it is important how the mechanism works if the mechanism really is what they're responding to. So if they're flapping their wings to dissipate heat, how does the structure of the wing allow them to do this, and why would they need to flap their wings to dissipate this heat better than if they just left their wings in one place, is the question. And it has everything to do with the structure of the scales.
Well, I know the scales actually reflect some of the sunlight.
They can, it just depends on the color of them, but
Yeah.
it's more structural than that. And let's just move on. You guys didn't figure this part of it out, so.
Can you go back to your one of your introduction slides? You talked about, you said something about how organisms should forage in the least costly way. And I was wondering if you could give me some examples or describe that a little bit more. Of what it would look like to forage in a least costly way.
So if there's not like a lot of nectar, say a butterfly's in like a patch like right here, and there's not a ton of nectar available, then the butterfly maybe shouldn't be like searching as hard or like flying around as much, since if they have to like stay in this patch, like theoretically. So they shouldn't like fly around as much and like search as hard because there's less nectar available. So by searching harder, you're gonna lose, you're not gonna gain very much energy.
What the marginal value theorem says, if there's not much nectar there, what should you ultimately do?
You should leave.
You should leave and go someplace else.
Are there any other examples?
I mean, there's the obvious one that if you're in a patch, and there's a patch over here, and this one has a little bit less nectar than this one, the butterfly is not going to fly over here just to get a little bit more nectar. It's going to stay here and get as much nectar out of this patch as it can before it moves on to the next one.
It's actually not what the marginal value theorem says. If the patch is right over there and it's really as close as you're saying it is, they would go to the next patch and gain more energy per unit time, and they would deplete that patch until it equals the amount of energy gained from the patch that they left because it wasn't as good quality. And the marginal value is just kind of the average value of all of the patches in the area. And if you're getting more energy gain than the marginal value, you stay in that patch, and as soon as your energy gain drops to that marginal value, you pick up and leave and go someplace else, assuming that the costs of moving from one patch to another aren't significant, although that's all factored into things. So if patches are really close, then even a small gain in energy someplace else is worth moving because the travel costs aren't significant.
So what's the connection between these ideas about foraging and your study? 'Cause
I believe that it was just kind of unclear to us why butterflies would be beating their wings while on the flower, just in general, because they are dissipating heat. I mean, while they're foraging, or while they're consuming this nectar or food or whatever you'd like to call it, they're going to be gaining energy. But if they're beating their wings, then they're at the same time losing energy. So why would they not just remain at rest and gain even more energy from the process?
So this was just more like looking into, like for us to try and understand foraging better, considering I thought of why would you waste energy. It kind of goes back to like the hummingbird example, like why would you fly to like maintain your, why would you forage while flying or when you could forage while like sitting on a branch?
Would that have something to do with metabolism, since these animals are ectotherms and metabolism is often temperature related? Would they have to stay at a certain temperature to be able to metabolize and after they're moving?
That's a good
That's
question.
a good
We'll
idea.
have to look into that.
I'm done. And
Yep. All right, thank you guys.
Right.
Bye, Katie.
Hi, Katie.
Good luck, Katie.
Thank you.
Where are you guys playing?
St. Louis. Yeah.
Oh, yeah. Sorry, I was taking notes.